Hi, everyone. In this video, I will be giving a demonstration of binary logistic regression using SPSS version 29. And before I get started, I do want to mention that underneath the video description, you'll find a link to the SPSS data file that I'll be working from in this presentation. So you can download a copy of the data to follow along. You'll also find a link to a PowerPoint that provides a lot more detail that I'm going to be providing in this video discussion. Quite frankly, a lot of concepts and so forth are rather complex, and to be as efficient as possible and as thorough as possible, I wanted to provide that for you. So feel free to download a copy of that PowerPoint to learn more. Again, the data set and the PowerPoint are both linked underneath the video description. So for this discussion, we're going to be using an example of binary logistic regression provided by Hosvon and Lomax in their 2020 text, An Introduction to Statistical Concepts, 4th edition. And the screenshot of the data that you see are provided on page 1000. So in this example, we will be predicting the probability of a child being ready for kindergarten as a function of household composition. That's a binary variable coded 0 for one-parent household, 1 for two-parent household, and social development. And that is essentially a score from a teacher-administered scale. It's treated as continuous in our model. So lower scores on the scale would reflect lower levels of social development. Higher scores would reflect higher levels of development. The dependent variable is kindergarten readiness. It's a binary variable, obviously, coded 0 for not ready for kindergarten, 1 for ready for kindergarten. So let's go ahead and open up SPSS and take a look at our data and then run our analysis. Okay, so here we have our data set. We have 20 children that are represented in this data set, so there are 20 rows of data. Our predictor variables are social development and household composition right here. Again, social development is a continuous variable. Household composition is a binary variable with coded values of 0 for one-parent household, 1 for two-parent household. And it's actually already in the form of a dummy variable with those values of 0 and 1. The readiness variable is our binary outcome, coded 0 for not ready for kindergarten, 1 for ready for kindergarten. So we'll go ahead and go to Analyze Regression and then go down to Binary Logistic. We'll move readiness, our binary outcome, to the dependent box. We'll move social development and household composition to the covariates box. Now, because household composition is a binary variable, technically we don't need to recode it or treat it as categorical in our model. But we're going to do this anyway, just to kind of show you how to do this. And particularly, it's useful in those cases where you have a multi-categorical variable with more than 2 levels. But right now, the household variable is already in the form of a dummy variable. So technically, it would not necessarily be. It's not necessary to do any kind of recoding. So I'm going to click on categorical right here, and we're going to move the household variable over to the categorical covariates box. And the contrast by default is set at indicator. And basically what it's going to happen is that if the variable is categorical, it's going to do an internal recoding of that variable into a set of dummy variables. And the number of dummy variables that would be included in your analysis would be equal to the number of groups or categories on that predictor variable minus 1. Well, because household only has 2 levels to it, there's only going to be 1 dummy variable if you were doing a recoding. So we're not really going to see much happen there. In terms of the reference category, the first option is selected by default. Basically, in this case, that would treat the one-parent household as being the reference category on that variable. If we had selected last, then the reference category would be the two-parent household, but we're going to stick with the first right here. So we'll click on Continue. If you click the Save button right here, what you'll see is you've got various options for predicted values, such as predicted probabilities and group membership. So the predicted probabilities that would be generated, they would be generated for each case, and it would be the predicted probability based on the model of a child being ready for kindergarten. That's our target outcome, if you will. Then based on those probabilities, we have a predicted group membership. So if the predicted probability is greater than 0.5, then the predicted group membership would be 1, which would be essentially that a child is predicted to be ready for kindergarten. If the predicted probability is less than 0.5, then the predicted group membership would be not ready for kindergarten. We also have options for influence diagnostics. So there's the analogy to Cook's D right there. We have leverage values, DF betas, and we also have the options for residuals. I'm just selected standardized right here. I'm not really going to spend any time in this video on going through all this, but I do have some discussion of these options in the PowerPoint. So I'll just kind of leave these clicked just so that you can see what happens to the data set once we've run our analysis. So we'll click on continue and then options, and then we'll select Hosmer limit show, goodness of fit, and then also confidence intervals for the odds ratios. So in your output, odds ratios for each of your predictors will be generated, which basically is reflecting the multiplicative change in odds with increasing values on your predictor variables. The odds ratio for the for the intercept is actually just an odds. Which is, the odds is just basically a ratio of probabilities. The probability of a target event, probability of A, divided by the probability of a non-target event, or basically the probability of B, or you could say probability of not A. So at any rate, we can also generate these confidence intervals for the odds ratios that are presented in our output. So we'll go ahead and click on continue right there and click on OK, and we generate our output. So looking at our output, the first part of the output, you'll see just kind of summary information about the model and so forth and the data. You'll see we had 20 cases that are included in the data. We have 0 missing cases right there. You'll see information about dependent variable encoding and also coding of the categorical variable. So there's not really a whole lot else to talk about right there. We'll move down. You'll see that it says block 0. And that's the beginning block. And basically, the information contained here really pertains to a model where there are no predictor variables. And if you look down here at the variables in the equation, this regression output right here, you'll see a regression model that's given, but only with an intercept. So this is an intercept only model. So there are no predictors in the model. And this is basically treated as a baseline that is a model that is compared against our full model later on. So the baseline model, our intercept only model, has no predictors in it, and we'll be comparing our model with our set of predictors against this model. You'll also notice that right over here, this percentage that's given right there, this is basically reflecting the percentage of cases that are falling into group 1. So if you think about y equals 0, those are cases that were observed to not be prepared for kindergarten. So we had 8 cases that fall into that group right there. So I'll just say n is equal to 8 right there. And then y equals 1, that's the outcome. That's the target outcome right here. So that would be the number of children that are prepared for kindergarten. And we had 12 children right there that fall into that group. So basically, if we just take the number of children that fall into the target outcome and divide by the total number of children, which is 20, that's what gets us this 60% right there. You'll also see that with the variables in the equation over here, this right here, this is basically an odds, or the odds that y is equal to 1, or the odds overall in terms of the odds of being children being ready for kindergarten. So in a nutshell, if we just take the 60% that we have up here, if we just say odds that y is equal to 1 can be computed as 0.6, and then divide that by 1 minus 0.6, or 0.4. So I'll just say 0.6 divided by 0.4. That's what gets us the 1.5. So it's just a ratio of probabilities. In this case, it's the probability of a child being ready for kindergarten to the probability of a child not being ready for kindergarten. So that's just kind of a general overview of this first part of our output. We'll scroll down and then we move into our model information. So when it comes to thinking about our model, we are generally going to evaluate our model in a couple of ways. We kind of start out by looking at the macro picture, so looking at the overall fit of the model, and then we move into looking at the components of the model. So the general strategy is very similar to what you would see in the context of least squares regression. In least squares regression, you look at the R-square value and the significance tests related to the R-square value to look at the overall fit of the model. And then you move into looking at the individual predictors in terms of their contributions to that overall fit. So it's the same principle at play in the context of logistic regression, but things do look a little bit different, and the overall indicators of overall model fit are going to look different. So we're going to start out by looking at the overall fit of our model with the likelihood ratio chi-square test. So I'm going to write down here likelihood ratio, or LR chi-square test. And that's the test that's given in this portion of our output. So the model chi-square test value is 15.793. The degrees of freedom for this test is 2. That's equal to the number of predictors. And then this is our p-value right there. So you can see that we have statistical significance. So the likelihood ratio test is basically the way it's set up is to compare a full model, in this case containing all of our predictors, against the null model, or our intercept only model. And so what we're doing effectively is testing whether our full model is a significantly better fit to the data than our null or intercept only model. So we find that we have statistical significance here, so we would determine that our model does fit significantly better than the previous null or intercept only model. Another way to think about this test is a test of the null hypothesis that all of your regression coefficients in your model are equal to 0. So if you reject the null in this case, as we do right here, then basically you would infer that at least one of the population regression slopes is not equal to 0. So there you go. The next piece of our output in terms of looking at the overall fit is this model summary table right here. So looking at it, you've got this -2 log likelihood. This is referred to as the model deviance. So I'll just kind of write over here deviance. And really by itself, the model deviance doesn't tell you a whole lot, but it does figure into other indicators of model fit. So that's why it's kind of useful to at least know something about this. So the -2 log likelihood, or the model deviance, is bounded on the low end at 0 and then extends to positive infinity in that direction there. And so basically a value of 0 is associated with a saturated model, basically a model that represents perfect fit to the data, and then values that extend towards positive infinity. As we move from 0 to positive infinity, the fit of our model is actually worse and worse. So the closer to 0 your deviance is, the better your model fits to the data. The further away from 0, the worse of a fit your model is to the data. Now you'll also see that we have these R-square values that are printed out in the model summary. You have Cox and Snell and Nagelkerke R-square. And these are basically, these are rough analogies to the R-square value that you would see in the context of least squares regression. And in fact, you'll see them referred to, and I certainly refer to them in my PowerPoint as pseudo R-square values. So they're not computed the same way as R-square in the context of least squares regression. Again, they're treated as analogies to that. The Cox and Snell, the upper bound of that is not going to be 1, or generally it's not going to be 1. The Nagelkerke R-square is actually an adjustment to the Cox and Snell, so that it falls in a range from 0 to 1. So the upper bound then becomes 1. I'll be honest, these are not my preferred pseudo R-square measures. Most of the time, my preference is to use McFadden's pseudo R-square. And unfortunately, in SPSS, at least going through this particular route, you're not able to obtain McFadden's. But I'll show you after I kind of run through all this part of our output, I'll show you how you can obtain McFadden's pretty easily. So at any rate, we'll scroll down. We'll look at the next piece of our output. We have the Hosmer-Limashow test. So you'll see right here we have the p-value that's given. This is also a chi-square test, but it's not the likelihood ratio chi-square that we saw previously. This is basically a chi-square test that's making a comparison between observed and expected frequencies associated with levels on the outcome variable. So that's what this box basically contains down here. And so the closer the observed and expected frequencies, the greater the fit of our model to the data. So if you find statistical significance, that's actually indicating significant discrepancy between those observed and expected frequencies. So that's actually an indication of lack of fit. So in our case with Hosmer-Limashow test, the p-value is 0.698. And because that's non-significant, that's actually regarded as a good thing with respect to the fit of the model to the data. Now, I do want to mention too, that thus far we've looked at kind of 3 or 4 different approaches to talking about the overall fit of the model. We have the likelihood ratio chi-square, we had the the pseudo R-squares, and then we have the Hosmer-Limashow test that's given right here. And not all of them are necessarily going to agree. So just think about each of these as different kind of vantage points or different approaches to kind of looking at the overall fit of the model to the data. But in this case, it is agreeing with particularly that likelihood ratio chi-square test that we had above. So next we'll scroll down and we'll take a look at this classification table. So the classification table that you see right here, this is basically looking at how well the model is doing in terms of prediction. So you'll notice that each row right here represents the outcome on the dependent variable, the observed outcome. So you can think about not being prepared for kindergarten. That is basically y is equal to 0. Being prepared for kindergarten, that is y is equal to 1. Okay, so those are the observed outcomes. So you'll see that the columns, these are predicted outcomes based on the model. And so in terms of predicted outcomes, you have the prediction that a child would not be prepared for kindergarten. So I'll just denote this as y hat equals to 0. And then the prediction that a child would be prepared for kindergarten, where y hat would be equal to 1. Okay, so there you go. So and just to kind of show you those predicted values, let's take a quick look at our SPSS data file. Okay, so now we're looking at the SPSS data file with all those indices that we generated. And so right here, you'll see that we have the predicted probability of a child being in the group 1, or basically being ready for kindergarten. So you'll see, like the first child right here, the predicted probability is 0.29. So because that number is less than 0.5, that child would be predicted to not be ready for kindergarten. The same goes for the second child. The predicted probability is 0.02. That child is predicted to be not ready for kindergarten. The third child, the predicted probability is 0.88. So the predicted group membership is 1, which is that child is predicted to be ready for kindergarten. And the same would go for the 4th child. So that's that's where these numbers are coming from in the table. Basically, the observed outcomes are the readiness values right here. So this is basically, y is equal to 0, y is equal to 1. These are the predicted outcomes. So that would be the y hat equal to 0, y hat equals to 1 that I was referring to looking at that classification table. So now looking at the table in a little bit more detail, you can see, again, we have y equals 0, y equals 1. Y hat equals 0, y hat equals to 1. Okay, so you can see looking at this that in terms of being not prepared for kindergarten, all the children in the first row in our data set right here, those are children that were observed to not be ready for kindergarten. So the total number is 8. Basically, if you take the 7 plus 1, that's the total number of children in this row that are predicted to not that are observed to not be ready for kindergarten. Then in terms of being prepared for kindergarten, we had 12 children there. So we had 12 children in the second row. Okay, so of the individuals that were predicted that were prepared for kindergarten, we had 11 that were correctly predicted by the model to be prepared for kindergarten. So if we take the 11 and divide by the total number of children that were prepared for kindergarten right there, then that gets us what's called the sensitivity for our model. That's the percentage of children or proportion of children that were correctly predicted to be prepared for kindergarten. So if you take the 11 divided by 12, you get 0.917 right there, and multiply that by 100%, and that's the sensitivity for our model. So the 11 is reflecting accuracy and prediction right there with respect to children being prepared for kindergarten. If you look right up here, you've got the 7. So you have 7 children that were 7 of the 8 children that were not prepared for kindergarten, that were actually predicted to not be prepared for kindergarten. So if you take the 7 and divide by the 8 in row 1, then that's what gets you what's called the specificity for the model. So if you take the 7 divided by 8, that gets you 0.875. Multiply that by 100%, and you can see right there, there's the specificity of the model. So in a nutshell, the sensitivity is telling us the percentage of cases in our target outcome group that were correctly predicted by the model to be in that group. So in this particular case, 91.7% of the children who were observed to be prepared for kindergarten were actually predicted by the model to be prepared for kindergarten. 87.5% of the children who were observed to not be prepared for kindergarten were predicted by the model to not be prepared for kindergarten. So that's the difference between the sensitivity of the model and the specificity of the model. There's another couple of indices that we can refer to as well. One of them is called the false negative rate. And basically, the false negative rate can be computed very easily by taking the misclassifications, in this case right here, of the children that were prepared for kindergarten. One child was predicted to not be prepared for kindergarten. So that's a false negative in terms of the prediction. So right there, we could take just basically dividing 1 divided by the number of children in that row, which is 12, and that would get us the false negative rate. So the false negative rate is basically 1 divided by 12, that's 0.083. So 8.3% of those individuals that were identified as being prepared for kindergarten were incorrectly predicted to not be prepared for kindergarten. So that's the false negative rate right there. And then for the false positive rate, we're just going to take the misclassification right here, the 1, and divide by the number in the row, which is 8. So in that case, that gets us 0.125. So basically 12.5% of the cases that were not prepared for kindergarten were predicted by the model to be prepared for kindergarten. So that's your false positive rate right there. In terms of the overall accuracy or classification accuracy of the model, that's easily computed just by taking the correct classifications here and here, summing those together, and then dividing by the total sample size. So we had basically 7 plus 11, that's 18 individuals that were correctly classified based on the model, divide by the total number of children, which is 20. So that gets us 0.9. So that's the 90% that you see right there. So next what we'll do is we'll move down and we'll take a look at the variables in the equation. So we're going to look at the individual predictors and their contributions to our model. So the first part of the output that I want to draw your attention to is the kind of the regression part, if you will. So in this case, you've got the regression coefficients here. There's standard errors. This is a Wald chi-square test. It's basically, if I take the regression parameter right here, divide by the standard error, and then square it, that gets me a chi-square value, and that's the Wald chi-square that you see right there. Each parameter is tested. Here we have degrees of freedom for each of those is 1. And the significance levels right there, those are the p-values for testing the individual predictor variables. Now, as you're looking at this regression portion, it's important to keep in mind that what we're trying to do is we're trying to model the predictive relationship between our predictors or independent variables and the probability of a child being ready for kindergarten. So predicted probabilities is really the outcome that we're trying to model in relation to the predictor variables. Now, we can't model those relationships using a linear function. And in fact, let's just say, for instance, I have, just to simplify things, let's say I've got just a single predictor variable. So let's just say we've got our predictor variable, let's just say it's social development or whatever X. Okay, so probabilities are bounded at 0 and 1. Okay, so if we try to model the relationship between our X variable and our outcome variable in a linear function, eventually it's not going to work, because what can happen is you can end up with values that are greater than 1 or less than 0. So it doesn't really make much sense. So a better model is more along the lines of an S-shaped function. So in other words, as we move from lower levels of our predictor variable to higher levels, what we'll see is the probabilities are increasing in this kind of fashion. And then you'll see that the probabilities are changing across levels of our predictor variable, whatever that is. In this case, I'm just kind of illustrating social development. So most of the change in the probabilities in terms of being in the target outcome group, or y equals 1, occurs nearer to 0.5. Whereas when you move to the ends of the distribution, towards the tail ends of the distribution, then they get, we end up with probabilities that are getting, they're changing less and less. So as we move in this direction right here, the probability of being in group 1 is increasing still, but ever so slightly as we move to higher levels on our predictor variable. If we're moving kind of in this direction right here, the probabilities as we get closer to, as we are kind of moving in this direction along our predictor variable, the probabilities are getting closer to 0, but the changes in those probabilities are getting smaller and smaller. So that's essentially, so in order to model the relationship between our predictors and the predicted probabilities, we have to utilize a transformation of those probabilities. And that's the way that we do that is we convert those probabilities into odds and then log odds. Okay, so that's essentially what's happening. So what you see right here in terms of the regression coefficients, it's reflecting a linear function, but it's reflecting a linear function between the predictor variables and a transformation of the probabilities into log odds, which are referred to as logits. So you'll hear that term in the context of logistic regression. So the regression slope that you see right here for social development, 0.967, basically means that for every 1 unit increase on social development, the predicted logit changes, or in this case, because it's a positive slope, is increasing by 0.967. The household regression slope that you see right here, it's negative 6.216. Because we only have 2 levels of that particular variable, basically what that's indicating is that the predicted logit for a child in a 2-parent household is 6.216 points lower than the predicted logit of a child in a single parent household. So as you're thinking about it, obviously, you know, that most folks are not really familiar with the thinking in terms of logits. And so if you want to think about this way, just kind of look at the sign of those regression slopes. If it's a positive sign, you can logically infer that you know, as we move from lower scores to higher scores on our predictor variable, that that the predicted probabilities of being in group 1, basically our target outcome group, are increasing. So in other words, because social development has a positive slope right there, that's basically telling me that as we move from lower levels of social development to higher levels of social development, that the probability of a child being prepared for kindergarten, those probabilities are increasing. For the household variable, because that slope is negative, what that's basically telling me then is that again, because this is a binary variable, that the probability of a child being prepared for kindergarten is actually lower if they're coming from a household with 2 parents as opposed to 1 parent, which logically that doesn't really necessarily make a lot of sense, because there are a number of factors that can go into this. But you know, on the average, the expectation might be kind of the converse to that. But nevertheless, I mean, this is fake data, so you just kind of have to kind of work with what you got here. So at any rate, looking at our significance test, you can see that our p-value is equal to 0.03. That's obviously less than 0.05 for the social development predictor variable. So that would be a significant predictor right there. And then for the household composition variable, p-value is greater than 0.05. So using that conventional alpha, this predictor would not be considered statistically significant. If we look at the EXPB column right there, these 2 values right there, the 2.631 and the 0.002, those are odds ratios. So the constant, the intercept down here that you see in this model, in our linear portion of our model, the constant, or the intercept, that is essentially the predicted logit for a case that has values of 0 on both of the predictor variables. And if you exponentiate that, that's what's going to get you this number right here. And this is actually not fully 0, it's just very close to 0. But basically that would be the odds of a person you know, who scores a 0 on social development. And on the household variable, that would be 1 parent household in terms of the coding. That would be the odds of being prepared for kindergarten. But the other 2 values are odds ratios, which is reflecting the multiplicative change in odds per unit increase on the predictor variable. So you can see right here for the odds ratio for social development, the 2.631, that just basically means that for every 1 unit increase on social development, the odds are increasing by a factor of 2.631. The odds for the household variable is 0.002. And basically that just means that the odds for being prepared for kindergarten for children who are in a 2-parent household are 0.002 times the odds of a child coming from a one-parent household. So that's kind of the way to interpret that. And then again, I want to kind of draw your attention back to the PowerPoint because I do go into a lot more detail. This is just kind of a quick overview of some of these results, but the PowerPoint does contain a lot more detail. The last portion right here, this is a confidence interval for the odds ratio. So if you could theoretically, just report the odds and the confidence interval and use the confidence interval to test the significance or the statistical significance of the odds ratio. The odds ratio, the null hypothesis for the odds ratio, let's just denote it as psi is equal to 1. The alternative hypothesis being, psi not being equal to 1. I'll just say not equal right there. And so if 1, the null right here, if it falls between the lower and the upper bound for a confidence interval, then in that particular case, that would be an indication that the odds are 1, in which case that means that there's no relationship between the predictor variable and the predicted probabilities of being in group 1. So you can kind of think about it from that standpoint. And basically, again, an odds of 1 just indicates no relationship. So in our first case right here, you got 1 does not fall between the lower bound of 1.097 and 6.313. So in that case right there, social development is a significant predictor, and the odds, basically the odds ratio is statistically significant. For the household variable, the odds, the confidence interval ranges between 0 and 1.693. So the null odds falls between the lower and the upper bound, making household a non-significant predictor within the model. Okay, the last part that I want to highlight is getting, how you can obtain that McFadden's pseudo R-square value. That can easily be accomplished. We'll just kind of go back into the main output right here. Just to reiterate, there's our predicted probabilities and predicted group memberships. These are those regression diagnostics that I was talking about before, and again, I go through that in some detail in the PowerPoint. But to get the McFadden pseudo R-square and some other indicators of overall model fit, we can actually kind of trick the program by going through regression and then going down to multinomial logistic regression. So typically multinomial logistic regression is still logistic regression, but it's utilized in those cases where you have where you have essentially a non-ordered categorical variable, typically in those cases utilized with nominal variables that have more than 2 levels. But we can also use it here in our case where we have just 2 levels of our dependent variable. So I'm going to click on multinomial logistic right here and kind of reset this a bit. So we'll click on readiness as our dependent variable. We'll click social, move it down to the covariates box. Household, we can either, we can move it to the factor box. The one downside with this is that in this particular case, going through this menu right here, the household, the reference category would actually be the last category on household. So, and that category is the 2-parent household. That's not going to affect the overall fit of the model, but you'll see a little bit of a difference with the results that we had generated previously. But if we want to generate the same results, we can easily do that because household is already already in dummy coded form. So we'll move this out and just kind of move it down to the covariates box right there. We also want to make sure that with the dependent variable, we have a reference category. So in this case right here, I'm going to click this button right here. And like I said, most of the time, multinomial logistic regression is utilized when there are 3 or more levels of the dependent variable. So it kind of makes it maybe a little bit more sense to give you more options on the reference category there. But we're going to select first category right there to keep it consistent with our binary logistic regression, where the not being prepared for kindergarten was our baseline, our reference category, and being prepared for kindergarten being our target outcome. So we'll click on continue, and you'll see that changes to first right up here. Then we'll click on model. We'll click on statistics, and we'll click on, I'll go ahead and click on information criteria. There's classification table. There's goodness of fit right there. So we'll click on those, and we'll just stick with that. So we'll click on OK. And so you'll notice that in terms of the information that's provided, first off, you'll notice up here we have our likelihood ratio chi-square test. So there's our degrees of freedom and significance level. This is the same test that we started out with previously through the other menu system. You'll notice that basically you're making a comparison between the intercept-only model or null model and the final model that contains the full set of predictor variables. And I'll draw your attention to the fact that if you recall me talking about the -2 log likelihood, that being the model deviance, well, we have the model deviance for the intercept-only model and the model deviance for our full model. So if you just take the difference between these two, if you take the 26.92, which is indicating the worst fit, remember deviance is bounded at 0, and as values get larger and larger, that signals worst fit. So here the model deviance for the intercept only model is clearly larger than the model deviance for the full model. And if you subtract the model deviance for the full model from the deviance of the intercept-only model, that's what produces the chi-square value that you see right here. You'll see too, we've got goodness of fit, other goodness of fit tests right here. We've got Pearson's chi-square goodness of fit test and a deviance chi-square goodness of fit test. And basically, the way that these are interpreted, in a nutshell, if you have non-significance, that's an indicator of good model fit. So both of these tests are actually non-significant, which is consistent with the proposition that our model is a good fit to the data. We see the pseudo R-square values that we have right here. These are the same ones that we had seen previously with respect to during our earlier analysis. And then we have McFadden's pseudo R-square right here, which is 0.587. So, I mentioned earlier about my preference for McFadden's, and basically you could think about it this way, that, that McFadden's, I'll just say McFadden's right there, pseudo R-square, is essentially computed as a proportionate reduction in lack of fit from our involving our current model relative to the intercept only model. So in other words, we could basically specify it kind of in the following way. So basically it is computed by taking the deviance for the null model, subtracting the deviance for the full model, so taking that difference and then dividing by the deviance for the null model. So in a nutshell, we're just taking this chi-square difference right here and dividing it by this deviance right there. And so when we do that, we end up with the 0.587. So that would be the proportionate reduction in the lack of fit with our full model relative to the null or intercept only model. Or if you want to reframe it too, you could also say it's a proportionate improvement in fit of our full model relative to the null model. So I will also draw your attention in this output to these likelihood ratio tests up here. So oftentimes these tests can be more powerful tests of the predictors in the model than the walled chi-square tests that are found down below, and which we had seen previously in our other output. So basically these are what amounts to be likelihood ratio tests of the individual predictors. So the likelihood ratio test, let's say for the social variable, would involve comparing the fit of the model that contains both the social and household variables with the fit of a model where social is removed. So the change in fit is reflected in that chi-square test value that we see right here. And so you can see right here it's statistically significant. But notice the p-value that's given right here is less than 0.001, whereas previously it was 0.03. So you can see that the test of this predictor is more powerful using the likelihood ratio test than the walled chi-square test down below. If we look at the household variable right there, then the chi-square value right there is reflecting the difference in fit between a model that contains the social and household variables and a model that removes the household variable and just leaving the social variable. So we have the likelihood ratio test there, and we have our significance value. The p-value is 0.023. Previously, it was 0.071. So you can see again that the likelihood ratio test result yielded a more powerful test than the walled chi-square test that we saw in our parameter estimates table. So that's just something to consider when you're carrying out your test. You have the option of using the walled chi-square or the likelihood ratio test. My guess is probably most folks end up using the walled test because it is more conventional, and because when you run the analysis using the standard logistic regression menu, the likelihood ratio tests are not provided. But I'm just letting you know that is there in case you wanted to use those tests. Then finally, you can see at the bottom we have the classification results. That table is given as well. Okay, so that's going to pretty much do it with respect to this video presentation. Like I said, there's a lot to cover with logistic regression. Please be sure to download a copy of that PowerPoint. There's a lot more detail in there than I really could go over efficiently and effectively in this video. So I hope you do download it, and I appreciate you watching. So you guys have a great day and take care.